Okay, let's unpack this. We're doing a deep dive today into source material that argues for, well, not one, but two really disruptive shifts in how we generate power.
Hmm.
We're talking about some radical ideas here, ideas that really challenge the basic economics of energy.
Right. They're all about moving away from these systems that depend on, extreme purity and massive industrial scale.
And instead pointing toward what? Simple physics and cheap common materials.
That's a perfect way to frame it because what makes these sources so compelling is how they marry these hard scientific claims.
Claims like getting incredible electrical output from just tiny amounts of water.
Exactly. They marry those claims with a really strong critique of our current industrial dependencies. The whole idea is that, accessible science and common materials could be the real path to democratizing energy.
So our mission today is to explore those two big claims. First, this surprising, almost unbelievable idea of harnessing measurable, sustained electricity from microdroplets of water.
Just through something called capillary action.
And second, the argument that the age of silicon in solar power is, well, it's coming to an end, and it's making way for this game-changing material called perovskite.
We have a lot of ground to cover. We're going from microscopic physics all the way up to global supply chains. So let's start with the smallest claim.
But maybe the biggest breakthrough.
Yeah, exactly. The power you can apparently generate from just one tiny drop of water.
Right, so the source material, it details this experimental setup. They generated measurable electrical energy using what they call very tiny water droplets. We're talking microgram scale.
All leveraging simple capillary action. And when you say measurable, they gave some really specific, pretty dramatic readings.
They did. The measurements were quite precise. The setup showed a voltage of 520 millivolts, and another reading came in at 460 millivolts.
But the real jaw dropper, I think, is the current, the amperage.
Yeah.
They recorded it fluctuating, jumping between 3 million amperes and, at its peak, a massive 10-minute A.
10 milliamperes. Just to give you some context, if you're pulling 10 millima from a tiny water sample,
Hmm.
that's huge. This isn't just some flicker.
No.
It's a sustained output.
Yeah.
And the mechanism they propose is what makes it so revolutionary. It's not a chemical battery reaction, it's physics.
Mm-hmm. It all relies on this capillary action causing the formation of hydronium and hydroxide ions.
And that's the key step we need to unpack for you. When we talk about generating electricity from water here, we're not talking about electrolysis.
Right, which is using electricity to split water. This is the opposite.
We're talking about the water molecules,
Mm.
HO, being physically stressed by that capillary force.
Mm.
The water is being pulled up into a narrow space.
Think about it like this. When the water is being actively pulled in like that, the surface tension is enormous. That physical stress on the HRO molecules right at the interface where the action is happening, it's so intense it actually starts to kind of tear the molecule apart temporarily.
So that stretching and tearing, it strips a proton, an H+, away from one water molecule, leaving behind a negatively charged ion.
A hydroxide ion, OH-. And that loose proton, it quickly attaches to another water molecule, creating the positively charged hydronium ion, H+.
And the continuous sort of physical stress from the capillary pull separates those positive and negative ions.
And that separation, that directional flow, that is what generates the measurable electrical current.
So you're essentially turning the water interface into a power source. And it's fueled by surface tension, by physics, not by using up some chemical.
Exactly. And that brings us to the sustainability claim. They weren't just getting power for a minute or two.
No. The
Yeah.
experiment reportedly sustained this generation for a really impressive amount of time.
40 to 48 hours.
2 full days.
Yeah, and that sustained output is critical. The source links it to vaporization, to steam. As the water slowly vaporizes, the surface tension and the capillary action just keep refreshing the process.
So if this holds up, 10 LMA from a microdroplet for 2 days is, well, it's highly unusual. It suggests a renewable kinetic process, not a finite chemical one.
Right, and that magnitude and duration, that's what makes you look closer at the behavior of the electricity itself.
This is where we get to the core evidence they use to prove their claim. To prove this is sustainable generation and not just a chemical discharge.
The jiggling effect.
The jiggling effect. They describe the amperage readings constantly varying, sometimes instantly, even when the setup is completely still.
It's not a smooth current. It jumps around 4, 5, 9, 10 MA. It's erratic, kinetic.
And why is that jiggle so important? Because as the source argues, a standard chemical reaction, it follows a simple rule.
Right. It starts strong, it uses up its fuel, And the output has to, by definition, steadily decrease over time.
But if you see an output that's sustained, and especially one that keeps fluctuating upward,
It means something is actively replenishing the system. And that replenishment must be kinetic. It must be driven by that constant physical stress of the capillary action, renewing the ion separation.
it's happening faster than the system can deplete itself.
Exactly. The fact that the output goes up after a dip is argued as definitive proof that this is sustainable power generation. It relies on physics that's constantly resetting itself, not on chemical decay.
It's a really compelling distinction.
It is.
Now, this source material also had a very unique aside. It used the scientific process itself to make a tangential but pretty pointed social commentary.
That's right. The speaker included this fascinating detail about the measurement itself. They said the device, when charged, stores about 600 millivolts.
Okay.
But the moment you hook up the multimeter to measure it, the meter instantly steals 100 to 150 millivolts just by being activated. It drains energy just by trying to quantify it.
And the source uses that observation, the measuring tool taking a cut of the energy, to draw this broader political metaphor.
They do. They compare it to governments stealing or powerful nations stealing resources like oil and lithium from weaker nations.
And just to be clear, we are being strictly impartial here, just reporting what the source says. But using a scientific observation as a metaphor for resource extraction is certainly unique.
It definitely gives you context for the perspective that's driving this research. It's a clear sign that the speaker sees their energy breakthroughs as a way to disrupt these industrial dependencies that, in their view, enable that kind of thing.
And just to wrap up the science of the water part, the speaker also used some specific Tamil terms to describe the capillary action. They called it Thandugai Kavarchi, or Kavarchine Uli Izukal.
And that second term, Kavarchinai Uli Isukal, it translates to something like the pulling inward or attraction.
Which is a crucial detail.
It is, because it reinforces the point that this mechanism isn't passive. It's not just a damp surface. It's a constant, active physical force, the water being pulled inward, that supports the claim of sustained electrical output. The physics is doing the work.
And that shared principle, leveraging simple physics and abundant resources, is actually the perfect transition to our second deep dive today. The chemical challenge to silicon. We're moving from microdroplets of water to the multi-billion-dollar solar industry.
Right. We're shifting to this really strong, almost evangelical advocacy for perovskite, specifically referenced as calcium titanium oxide as the material that's going to dismantle the dominance of silicon in solar.
And they don't say it might happen. They say the end of silicon's reign is imminent.
Yeah, that it's coming.
So let's ground this for you. What exactly are we talking about when we say perovskite? Chemically, it's calcium titanium oxide, a specific mineral structure.
And it had a history. The mineral was first discovered way back in the 1830s in the Ural Mountains in Russia.
Right.
It was named after a Russian mineralogist, L.A. Perovsky. And interestingly, the source mentions the scientist was associated with discovering Thadi-Wugel, which in context, it translates to dense or hard formations. So this material has been known for nearly 2 centuries, but its use in solar is incredibly recent. It's really only taken off in the last decade.
Now, they really don't pull any punches when they talk about silicon.
No, they don't.
The source material is just unsparing in its critique. They call silicon dangerous, tremendously expensive, and say the cost is entirely driven by its insane demand for purity.
They make this truly dramatic claim, saying silicon needs 100%, 200% purity, a requirement so intense that trying to meet it has ruined nations.
That's a powerful statement. And it does raise the question, why does silicon need to be so incredibly pure?
It all comes down to quantum physics, actually. A silicon solar cell works by using energy from sunlight to excite electrons across something called the band gap in the crystal.
And for that process to be efficient, to convert light into electricity, that crystal has to be almost perfect.
If you have impurities, even tiny ones, they act like little defects. They create traps for the electrons, and they mess up the highly ordered structure.
Those flaws destroy that clean band gap.
Yeah.
The energy transfer becomes super inefficient.
Exactly. So to avoid those traps, industrial production has to go for this ultra-high purity silicon, which needs massive amounts of energy and very specialized, very expensive factories.
So the biggest barrier to getting into the solar industry is basically the cost of getting that near-perfect purity. And this is why perovskite calcium titanium oxide is generating so much excitement.
This is where perovskite just throws the rulebook out the window. The core claim, the most important claim, is that it works effectively even with impurities.
It doesn't need that maximum costly level of purification that silicon demands.
They literally call this impurity tolerance its greatest thing. It's an advantage that goes way beyond just chemical stability. It means the whole manufacturing process is fundamentally different and simpler.
And if you connect that to the bigger picture, the economic implications are they're immediate and they're massive.
Perovskite is described as very cheap. By removing the need for all that complex, energy-hungry purification, I mean, think huge clean rooms, vacuum furnaces, complex chemicals, you're slashing the costs.
Both the initial investment and the operational costs.
Right.
When I read that claim about silicon needing 100%, 200% purity, it reminded me of that saying, purity is the enemy of profit.
Yeah.
But here, the source claims purity is the enemy of global access. Because if you can make solar cells cheaply and effectively in less sophisticated plants, then suddenly solar manufacturing is open to a huge number of new players.
And that democratization potential is the ultimate conclusion of the source. If perovskite fulfills its promise, it doesn't just mean cheaper solar panels. It signifies the absolute end of the reign of silicon.
The whole philosophy shifts.
It really does. You're moving from systems that demand centralization and technical exclusivity, high purity, expensive materials, to using alternatives that are cheap, impurity tolerant, and accessible to anyone with just basic chemical processing.
Okay, let's just pull back for a moment and look at both of these ideas together. On one hand, we have a claim that we can harness continuous power from simple water using sustained kinetic physics.
Capillary action.
And on the other, a claim that we can revolutionize solar power with a simple, abundant mineral that doesn't require decades of complex industrial work.
Both concepts share a common, powerful critique of the status quo. They challenge the idea that energy breakthroughs have to be complex or resource-intensive.
Or rely on scarcity.
Right. Whether that's ultra-pure silicon or some specialized fuel, they argue that the complexity and expense of our energy systems aren't necessary evils. They're just artifacts of old industrial habits that new science can simply bypass.
So what does this all mean for you, for the listener, and the future of power? It might mean that the technology that powers your world won't be coming from the biggest, cleanest, most centralized facilities.
It might be coming from systems that just harness the simplest forces all around us.
They point to a future where every day, accessible things like slightly impure water and common oxides become the engines of power.
And if the claims about the capillary device's output and perovskite's impurity tolerance hold up, we are looking at a fundamental shift where energy independence becomes a real possibility for communities and nations that are currently locked out by the complexity of today's infrastructure.
That's immense food for thought. If the future of sustainable energy lies not in technological complexity or endless refinement, but in leveraging simple physics and abundant, impure materials all around us, what other industrial dependencies that shape our world might be on the verge of collapsing? Something for you to mull over until our next deep dive.